For people who don't know me, I'm Montaser. You can call me Monta. I'm a first-year PhD student working with Mike Bowling. Today, I'm going to be presenting Learning to be Cautious in a collaboration with Dustin over there, Alex, Yash, and Mike. So let's consider kind of you have a self-driving car. So this kind of self-driving car, it can be taking the images from the surrounding environment, and according to those images, it's going to take decision either, let's say, to make a turn, to brake, or to accelerate. So you train the self-driving car in San Francisco, which is going to be sunny all the time, and someone put it and bring it to Edmonton in the middle of the winter, which is the snow now. So what's going to change that? The snow going to change the appearance of the road. And actually, that will cause a problem because this car never saw snow in the road before. But as a human driver, maybe for me, when I first drive in the snow, which is I never drive before, before coming to Edmonton, I have this kind of situation that if I drive slowly, that means I will drive safely. But most of the learning algorithm doesn't have this tuition. So yeah, this is what's going to be the natural things to do. So the main goal of learning to be cautious is that we wanted the agent to learn to behave caution. We don't want the agent to behave caution only, but we wanted the agent to learn that behavior, that caution behavior without a human supervision and without kind of a human prior on that one. So before going deep into the details and how that's work and the experiments and the results and so on, let's try to play kind of a quick game. So again, I show an image over there, and you have 10 arms from 0 to 9. And if you select the correct arm, you get +1, otherwise you get 0. So I will start with the first 2 examples, and I will ask you guys to answer the following examples. So it's clear from this image, it's going to be 0, so I will choose 0. For this one, it's also clear that it makes sense to be 7. How about this one? What it looks like? Okay, yeah, reasonable. And what about this one? It could be 9 flipped as well. And what about this one? Maybe it could be one for some who have very bad handwriting like me. Two? Maybe. 7? What about this one? And this one? Could be. So going into the details, first we have to distinguish between 2 kinds of uncertainty. First is alloteric uncertainty. Basically, that's coming from the stochasticity of the environment. So for example, you're rolling a dice, and you don't know what is the next outcome of this dice. It could be 1, it could be 6, it could be 5, it could be 1. The other kind of uncertainty is the epistemic uncertainty. Basically, that's coming from the lack of the knowledge. So for example, you never saw dice before, so you don't know how many faces are there. Maybe it has 4 faces, maybe it has 6, maybe it has 0 in it. So the epistemic uncertainty basically coming that I know something, but also I don't know other samples as well. So back to the digits actually examples, the one with that we are familiar with is actually the digits, but the one that we are not, we kind of novel to it is going to be the shoe. So basically the assumption here is that in the novel situation, the reward is going to be undefined. Like, for example, if I go back to the shoe example and ask you, what is the reward of selecting arm number 4? No one will answer me that question because the reward is undefined for those arms. And also kind of, we are working on a particular setting where you train your agent, and it's now time for deployment. So there is no training. So we are not working on continual learning, and we are not doing any kind of adaptation. This is basically most of the RL actually application now, like you train an agent and you just deploy it in the real world. So we are not doing any kind of adaptation. So people try to actually to tackle this problem, to behave safely actually when you face something newer. There are several related work in this area. One of them is actually the constraint MDB. Basically, that's going to be, okay, I will try to constrain, let's say, the state action, or I can try to constrain the agent not going outside the state and so on. Another thing is going to be you kind of hand design the safety mechanism. So if the agent saw, let's say, snow in the road, try to drive slowly. But the problem with that, you cannot encounter all the situation, and you cannot design a safe behavior in all situations. So it's impossible to encounter all that situations. The third one is also the risk-averse RL. Basically, most of the literature in the risk-averse trying to tackle the alloteric uncertainty. So how are we going to do that? Basically going to be in two steps. First, we wanted the agent to identify the novel situation. Later on, we would like the agent to react safely to those novel situations. So how the agent actually gonna identify those kind of novel situation? The idea is actually you train ensemble of neural networks. So if we take just a single neural network, the input for this network, let's say, gonna be the image you passed it, and the output gonna be what is the reward of each action. So going back to the MNIST example, we passed, let's say, an MNIST digit, and we asked the neural network what is the reward of pulling arm number 1, what is the reward of pulling arm number 6, and so on. But we are not training a single network, we're training a bunch of neural networks. So what the outcome gonna be that all those neural network gonna agree if you pass something from the training distribution. If you pass something familiar to them, all of them can agree on the value of that one. But if you pass something different, for example, a shoe, as you can see here, some of them, okay, will say, for the arm number 4, I think the value going to be 1. Others will say, no, for arm number 7, it's going to be -1. So you got those high variation for that one. So the idea is that all this neural network will collapse. The value of the reward going to collapse for the familiar one, but you're going to have a high variation for the novel situation. So this is the first step. We wanted to build this kind of uncertain distribution. The second step going to be we trying to optimize the conditional value at risks. So conditional value at risk simply going to be, I would like to optimize this % of the worst case scenarios. So there are several ways to do that. One of them is to use KFN. So KFN is basically a two-player zero-sum game where you have your adversary trying to give you a hard time. So basically you sample in, let's say, sample, and your adversary will gonna give you the worst K, let's say, samples from the one you sampled before, and the agent trying to get the best out of that one, trying to optimize the best for that one. So here you have two values, n and k. So n and k are integers, and is always larger or equal to k. So for example, if k equal to n, that's me, like say, you're going to be optimizing the whole distribution. That's basically what is the risk neutral thing. But if k is way less than n, that's mean you're optimizing, let's say, the worst case scenarios, and this is going to be the caution one. So just to recap, the methodology is going to be simple. First of all, you build this you build this uncertainty distribution, and next you're going to optimize conditional value at risk for those one. So anyone have any questions before jumping to the next slides? Cool. So let's jump to the experiments. So in the experiments, if you remember the game we played before, we have this image, and we also say the agent to pull an arm from 0 to 9 for that one. But we're going to add a small thing. Here we're going to add kind of an additional action. Quote unquote, we call it help. It's just going to be an action. The reward going to be simple. If you pick the right arm, you will get 1. Otherwise, you will get 0. Except for the last arm, which is we call it help, you get a very small reward, whatever the value in this scenario is 0.25. So what do you expect? What do you expect? Like when we pass something familiar for the agent should pick, let's say, the number corresponding to that image. But when we pass something novel, the agent should try to pick the last arm because it has a fixed reward all the time comparing the other one. So that's exactly what happened in those results. So the y-axis here present actually the frequency of selecting the help arm. And here we have fashion MNIST and eMNIST. So each star here is an individual run, and this part representing the mean. And here we're comparing different value of k and n. So for example, 1 of 20, that means k equal 1, n equal 20, basically optimizing the 5% worst scenarios. 1 of 20, that means you're optimizing the 1/10 of the worst case scenarios. And also we have optimal R. This is basically what is the normal RL will do. Is going to be greedy to expected value for the whole distribution. So as we can see here, let's consider fashion MNIST. Basically, 1 of 20, which is the most caution policy, is actually selecting the help arm almost over 90% of the time. But as we turn down the caution, like for example, 1 of 10, which is less caution comparing to 1 of 20, is actually selecting less than that. And the same apply for 5 of 10. So as you can see, when we turning the caution to be down a little bit, the percent of selecting the help arm actually reduced. The same thing apply for the eMNIST. The thing is that if we compare eMNIST and fashion MNIST, we can see for the same, let's say 1 of 20, that 1 of 20 for the fashion MNIST selected the help arm more frequent to comparing to eMNIST. Why is that? Because actually eMNIST is actually letters, and there are some letters looks very similar, if not identical to numbers. For example, O and 0. So if I show you O and 0, probably that looks the same. L and 1, Z and 2, and so on. So those letters actually looks very, very, very similar, if not identical to those numbers, and that's why the most caution policy selected the help arm less for that one, because in those particular letters, they gotta be selecting the digits that corresponding or looks similar to that one. But someone could say, okay, in the scenario you just mentioned now, I could just build a classifier out of distributor classifier, and if the sample of out of distribution, I will just select the help arm. That's correct. You could do the same thing for that one. But what about in this example, where there is no an obvious action to select? So in order to do that, there is no help arm. We just have 10 arms from 0 to 9. But the twist here is going to be that we change the reward function. So the reward here going to be a plus 1. That means for the 0, you get a reward of 1. So that means the smaller arms, 0 and 1, get a lower or smaller reward comparing to 9 and 10. For 8 and 9, which is going to have a larger reward. But also that's reward, you will get it if you select the correct arm for that one. But if you select the wrong arm, the penalty going to be also corresponding to that one. So the smaller arm have a lower penalty, and the larger arm have a large penalty for that one. So basically this is what the table saying. So for each arm, it says 0. If you get it correct, you get +1. If you get it wrong, you get -0.1. But if you compare, let's say, to 9, if you select 9 actually correctly, you will get +10. But if you select it actually wrong, that you're going to get -1. So the idea is here is actually if you are sure about, okay, I'm sure this is a 9, you're going to select 9. But if you are not sure, probably you're going to select a lower actually arm, because this is have a lower penalty comparing to arm number 9. So if we pass a normal or a familiar image, the agent should select the correct arm. But if we pass, let's say, a novel image, actually the policy should select the lower arm or the smaller arm, because that has a lower penalty. And that's exactly what this kind of figure is showing here. So the y-axis represent here what is the average action index. So lower is better. That means for the fashion, you can see that 1 of 20, the most caution policy, trying to select the smaller arm more frequent comparing to the, let's say, to 10 of 10, and also the optimal R. The same apply for the EM nest. So just to recap what we have before, the both experiment actually in multi-arm bandit and both of them in MNest. But the first motivation example we mentioned is actually about driving. So we did try to do a smaller version of driving, that one. So this is going to be driving grid work. It's a very simple environment. You have a car here in blue, you have 2 lanes over there, and you have some obstacles. And the agent actually have some speed, like 3 level speeds. And the action for the agent going to be either moving right, left, or kind of be accelerating or pressing the brake for that one. So during the training, the agent should actually drive as fast as possible. So what we did is actually during the training, there is no obstacles on the road. And during the deployment, we place obstacles randomly in the road. You can think of those obstacles as the snow we just mentioned before. So the agent never observed, let's say, obstacles in the road before. So what we imagine that if you are a human driver, probably you're trying to, you saw something look different, so you're trying to avoid that one. So we wanted the agent actually to try to avoid those obstacles during the deployment, even the agent never saw those obstacles before. Those results actually reflected here. So if we look into this to the middle figure, which is indicating the collision frequency, so how frequent this agent actually collide within obstacles in the road, you can see the most caution policy 1 of 20 colliding way less. It's even 8 times or 9 times slower comparing to the 20 of 20, which is going to be the expected value, also the optimal one. The same apply. As you can see here, as we turn down the caution, we become less caution, we collide more frequent. But some examples, like we kind of place the obstacles, actually 2 obstacles in the road, so there's no way you can avoid that one. So what do you expect? You expect it, if there is no way to avoid those obstacles, I will try to collide with the less speed comparing to colliding with the high speed. And that's exactly what happened here. As you can see to the one to the right, you can see 1 of 20, whenever it collides with a lower speed comparing to others, actually, the less caution policies and so on. So the takeaways from those examples or those experiments is that even the agent never saw an obstacles in the road during the training, but during the deployment, the agent actually tried to avoid them. And if there is no way to avoid them, the agent tried to collide with a lower speed comparing to the expected RL will do. So to conclude, the takeaways from this presentation are going to be that first, we design kind of very simple environments where we demonstrate that it's very important for the agent to learn to behave caution. It's not enough just to behave caution. The agent should learn to behave caution, as well as also we provide kind of be an algorithm that makes this agent learn to behave caution in different scenarios, and so on. Also, the takeaway going to be that the degree of caution, you can turn that by changing the value of K and N, because some applications require very high degree of cautiousness or safety, while other doesn't. So depending on the K and N value, you can turn that on and up. You can turn that down and up. And although we add another layer of safety, that will not replace actually the human judgmental. So we're not going to be replacing any human here. We're just adding a second layer of safety. And for the future work is basically going to be that we assume that the transition probability is fixed in the novel and in the familiar situation, which is unrealistic. If you think about the driving in the snow, it's going to be slippery, it's going to be different and so on. But in this particular in this particular project here, we assume that it's fixed, which is a realistic scenario. So we wanted to relax this assumption. Also, we train, in order to build the uncertainty distribution, we train a bunch of neural networks thousands of them. They are very, very expensive to train. So we're trying to reduce this kind of expenses by using other kind of epistemic neural network and to estimate the uncertainty. And of course, all those experiments you just saw now actually are tabular, so there is no functional approximation. Another thing we would like to look forward is actually to expand it to functional approximation as well as to continuous action space. Yeah, that's actually conclude my talk, and I will be happy to take any questions.
We have like a mic for questions. If you raise your hand, I'll just bring it over.
Could you remind me what the Optim R hat baseline was?
Okay, so the OptimRL is basically, since we train a bunch of neural networks, will take the expected value of all of them and just act greedy to those values, which is basically what the normal RL will do.
Manta, I can't remember the actual details of the experiment, so I'm going to ask you a question to remind me.
Sure.
Was it the case that the agent actually avoided the obstacles, or did it just drive slowly over them? Because one explanation for the collision frequency being down is just driving slower, so it just runs over less in general. So did it actually avoid things, or was it just going slower, so it just encountered less of them?
Okay, if I remember correctly, it's actually doing both, so it's trying to avoid, but also, as you just mentioned now, if you go back to, you can see the speed is way lower compared to that one. But the thing I remember correctly is actually when there's two obstacles in the road, which is basically happened with the collision speed, it collides with a lower speed for that one.
It's interesting. I can mentally think of how the ensemble neural network would learn that driving slower has less variance in the rewards. But it's not obvious to me how the ensemble neural network would say, here's a thing I've never seen before. It's probably bad. Let me not drive over it. So anyway, that's kind of interesting because I could see how it would drive slower, but it's not obvious to me why it would avoid things.
Yeah, if I remember correctly, it's actually doing pause. It's going to be sometimes avoiding, but also, as you see here, the speed actually is lower comparing to the other policies.
I'll actually interject with a question
Sure.
since I have the mic. I was wondering, what's the difference between the 10 of 10? I'm not familiar with K of n, but what's the difference between the 10 of 10 and Optim? Because I thought they would be the same, but in some plots, there's a bit of a difference between the two.
Yeah, so as I just mentioned, OptiRL is basically you take the expected value of all of the neural network you train, and you just act greedy to those means. So this is what is the optimal. But 10 of 10 is basically that you say, every time I will sample 10 reward functions, and I will optimize for all of them. And you repeat that actually until it converge. So that's basically the difference, is actually every time you sample 10 reward function and you optimize for all of them.
I see. So almost maybe like a statistical bootstrap
Exactly.
or something?
Yeah.
Okay, here.
I'm actually going to follow up on that same line of reasoning. So when you were sort of describing this K of n, you were mentioning the red one is 5%. We're going to be optimizing for the 5% worst case, the bottom 5% of cases. So what if I multiply the denominator and the numerator by 10? So now I'm 10 out of 200. That's also the 5% case, but I suspect that's going to have a pretty different look. And so I would suspect that the two blue bars, the difference there is that I'm first doing this statistical bootstrapping sort of thing, whereas in the other case, I'm actually directly doing the sample average. So if that was instead like 1,000 of 1,000, then maybe these two blue bars would look indistinguishable. Is that the correct intuition?
That's correct. Basically, it's going to be the variation because every time you sample 10 of them and you optimize for all of them.
Yep, that makes sense. One other question, following up on Mike's question now. So because it decreased the speed, I don't know this environment at all, but I'm guessing this means we just encountered fewer potential collisions because we're just not traveling as far. Is that right? So there's like less potential to have a collision. If I control for, I'm going to run the experiment for 6 miles of driving, however long that takes. If you turn the speed way down, are all these bars going to be the same for the collision frequency?
So by 6 miles here, you mean like the distance or the speed or what?
I mean like the distance. Like I will now run this environment. So there's 100 chances for me to collide with a thing, whatever this thing is that we're counting this frequency
got
of.
you.
And every single agent will have 100 opportunities to collide, regardless of how fast it's going. Are all these bars going to be the same, or is it actually learning to like swerve and not collide?
I think the intuition here for the ensemble probably going to be trying to drive slow. But maybe there's something interesting happen about avoidance. So probably I think for the speed, it's going to look the same, but for the collision, maybe it's different.
Yep, that makes sense. Thanks.
You're welcome.
Sure. So simple question. How are you training the different neural networks? Like, is the data different? Is it like are they all using the same data but different initialization, or how's that happening?
Okay, so the samples, basically all of them are actually randomly initialized. So everyone have a different initialization, but they're using the same data, same hyperparameters, same training, actually like procedure, number of episodes, and so on. So the thing is here is actually that they're going to converge to different weights. And that's actually will give you the high variation when you pass something novel. But those actually different weights are going to agree on the outcome, which will happen if you pass something familiar.
Only the initialization is different, the data is exact.
Yeah, the data exactly the same.
I have a very basic question. You're using some sort of adversary to train things, right? Like in let's say the 1 out of 20 things, the adversary presents the 5% worst cases, right?
So here there is no training. We optimizing. So given this ensemble of neural network, we optimizing, let's say, the lowest, let's say 5% of those one. So there's no training here. Training only happen for the neural network inside the ensamples. But what we're doing here is actually we're just going to be minimizing the regret. Actually, when you sample, let's say, 10 actually samples, and you optimize the lowest one for this one, given a fixed policy, and you update your policy for that one. So there's no training, just we basically minimizing the regret. So I'm not sure the training is the right term here or not.
Okay, I think I understand what's happening.
Okay,
Thanks.
thank you. There's a question here.
So I have a question about the ensembling. So what is the method of a ensembling you use? Is it like just taking the average of the outputs, or so was it equal weights, or any other method you use?
So you mean the initialization, or you mean the outcome of all of them?
Yeah, I'll come with all of them.
So we sample each one like a sample.
Oh, I see.
Yeah. So each sample, that's mean this is the outcome of this neural network.
Oh, got it. Thank you.
Yeah.
I'm just curious about the relationship between caution and reward. Like, as you turned up the caution, did reward take a big hit, or did it not really matter that much because, like, the worst case scenarios accounted for a big hit in reward?
So the reward here, if I understand correctly, that's mean in the familiar situation. That's correct. So for example, in the MNEST, when let's say 1 of 20 or 1 of 20, the most caution one, did that affect, let's say, the accuracy of selecting the correct, let's say, digit for the MNEST? The short answer, it does, but slightly. So for example, it turned from, let's say, 99.9% to 99.5%. So it does, but it's slightly. But you can ignore that one. Yeah. But I mean, I think the thing is here that we wanted the agent to behave normally in the familiar situation, but we wanted the agent to behave actually cautionally in the novel situations.
We have maybe time for one more question. If not, let's thank the speaker.